Hello viewer, I am Professor Harold Thomas. I am a professor in Department of Applied Geology, Dr. Hari Singh Gaur Vishwavidyalaya Sagar. Today, I will discuss about crustal melting and granitic magma. Deformation and magmatism are three main internal processes within the earth. It is known that melt of basaltic composition are generated in the low velocity zone, also called asthenosphere, which is nearly 70 km under the oceanic crust and nearly 180 km under the continental crust. Other source regions of basaltic magma are divergent and convergent lithospheric boundaries. Melt of granitic composition can only be generated in the continental crust. Yoder 1962 has proposed several mechanisms for magma generation, and every model is simply based on change of pressure, temperature and composition. Unlike a pure phase, a rock melts over a range of pressure and temperature, and the liquid produced on partial melting does not have the same composition as that of the original rock. This is true for both mantle and crustal rocks. The curve showing beginning of melting of a rock is called solidus, and the curve above which the rock system is completely liquid is called liquidus. Melting or partial melting occurs when temperature increases or pressure decreases, or if water influx occur. The effect of these three agents of melting, which are also of metamorphism, can be easily understood with reference to figure. It shows dry and wet solidus curve. S denotes solid, L denotes liquid of a crustal rock. For mantle rocks, material rocks, material A is below the solidus and is completely solid. By changing any one of the agents, we can perturb the situation so that melting takes place. First, when we increase the temperature without change of pressure, a rock is partially melted, but increase in temperature result into decrease in the density of the crustal or mantle rocks. This would result in upliftment of the earth's surface, meaning increase of pressure, but erosion could then decrease the pressure. Second, decrease in pressure in a crustal segments, as during crustal thinning, would also cause melting. This is familiarly called decompression melting, exemplified by the basaltic eruption at the mid-oceanic ridges. When the point A moves adiabatically, thermal insulted from its surroundings like a plume, melting ensues. Melting also takes place when the influx of volatile, mainly water, occurs during metamorphism. This would reverse the slope of the solidus. This wet solidus or water saturated curve is characterized by temperature reduction as pressure increase because of the vapor effect at high pressures. Significant volumes of granitic rocks in oceanic region precludes the possibility of granites generation by partial melting of mantle, pedotite or subducted oceanic basalt crust. This absence also precludes the possibility of production of large volume of granitic magma by differentiation of parental basaltic magma, because experiments have shown that 100 parts of the basaltic magma can give rise to only 5% of the granitic magma through fractional crystallization. Granitic rocks of batholithic dimension cannot thus form by fractional crystallization. The process of metasomatism involving addition of SiAl alkalis bearing fluids into the pre-existing crustal rocks and thereby transforming them into granitic looking rocks is untenable. This granitization process or metasomatism does not find support from thermodynamics and physicochemical data. Features such as X solution in alkali feldspar, zoning in plagioclase, and equal volume of quartz alkali feldspar plagioclase in most granitic rocks do not support metasomatism as a granite forming mechanism. The only mechanism for generation of granitic melt is anastasis or partial melting of crustal rock. The mechanism was proposed by Söderholm in 1907 from the field observation in the Finland region, where granitic rocks are intimately associated with mixed rock called migmatite. Here, high-grade schist gradually develop ports, organ, veins, and folded layers of granitic material, which when developed on large amount is found to contain relics of the schist. The total absence of muscovite as a primary phase and the occurrences of microstructures and macrostructures associated with melting, for example, crustal faces of plagioclase, igneous-like textures of lycosomes, rafts of unmelted rocks, and celeron in the leucosome suggest that only mechanism for migmatites formation and generation of granitic melt is anastasis or partial melting of crustal rock. This was first proposed by Söderholm in 1907. Söderholm show that melts of granitic composition can only be generated in the continental crust. Several mechanisms of magma generation have been proposed by Yoder 1964, and every process is simple due to change of pressure, temperature, and composition. Unlike a pure phase, a rock melts over a range of pressure and temperature, and liquids produced on partial melting have different composition. Partial melting of this material can occur if there is an increase in temperature. Temperature without change of pressure result into melting. When A moves adiabatically, melting also occur. The effect of these agents on melting can be understood with a reference to figure. It shows dry and wet solid curves of a crustal rock or mantle rocks. Material A is below the solidus and it completely solid. By change any of the agent, we can perturb the situation so that melting take place. When we increase the temperature without change of pressure, a rock is partially melted, but increase in pressure result into decrease in the density of the crustal or mantle rocks. This would result in upliftment of the earth surface, meaning increase of pressure, but erosion would then decrease the pressure. Second, decrease in pressure in a crustal segments as during crustal thinning would also cause melting. This is familiarly called decompression, melting, exemplified by basaltic eruption mid-oceanic ridges when the point A moves adiabatically like a plume, melting ensues. Melting also takes place when the influx of volatiles, mainly water, occurs during metamorphism. This wet solidus of water saturated curves is characterized by temperature reduction as pressure increase because of the vapor effect at high pressure. An atectic process for the origin of pegmatites and granite has been shown by experimental melting of rocks, mainly shell, gravex, schist and gneisses. Anodexis is the most important processes affecting the earth crust. As stated earlier, it occurs in the deep crustal granitic belt have obviously lead to the redistribution of elements in the crust. Furthermore, the nature of the source and the conditions under which anodexis occur determine the character of the resulting melts. This has been demonstrated by the laboratory experiments on melting of rocks. The first experiment was done by Peter Wiley in 1952, who reported a melts of granitic composition when shell was subjected to melting in hydrothermal experiments. Subsequently, Tuttle and Bowen in 1958 performed melting experiments on granite system SiO2, KAlSi3O8, NaAlSi3O8 plus H2O, that is quartz orthoclase albite water system. They experimented at different pressure, water pressure, and found that granite melting begins near 650 degree centigrade. Their results are shown in the phase diagram. In this triangular phase diagram, eutectic is located between quartz and alkali feldspar, while no eutectic occurs between two alkali feldspar because of the solid solution between them. Just like in plesioklase feldspar, one can think this triangular diagrams as a combination of the two component system, namely quartz albite, quartz orthoclase and albite orthoclase system. In this three phases system, quartz albite orthoclase with water, there occur a ternary minimum or cotectic minimum at which the last liquids on fractional crystallization tend to reach. The thermal minimum is found to shift towards albite corner with increasing water pressure. See Tuttle and Bowman 1958, when P water increases to about 4 kilobar. The cotectic minimum was found to become ternary eutectic. This will be the composition of the first melt formed from melting of any gneisses at 4 kilobar pressure. At this point, quartz albite orthoclase will coexist with melt and vapor. The thermal eutectic is also found to shift towards albite corner with increasing of pressure as shown by the further melting experiment by Lutz et al. 1964. These experimental results were applied to the origin of granitic rocks by Tuttle and his co-workers. These authors plotted normative quartz albite orthoclase of the available analysis of granites and rhyolites. The results are shown in figure A and B. These plots, when viewed in light of the experiments on granite system, demonstrated that first, the granites are a product of recrystallization from a melt, since the felsic portion of the most granite correspond to the ternary minimum or cotectic minimum, also called temperature minimum, and to the ternary eutectic. Second point, the rhyolite also showed their quartz orthoclase albite maximum near the cotectic minimum and thus coincide with the maxima of the granites. These evidences reject the hypothesis of metasomatism and support that the granite rocks are produced from crystallization of melt. Third, the composition of the first melt formed upon heating of any composition in the granite system. A mixture of quartz albite orthoclase phases would correspond to the composition of the ternary eutectic at the specific pressure. This is the consequence of the fact that minerals of the natural granites are always in equilibrium, hence ternary eutectic crystallization occurred, and that thermal equilibrium composition is pressure dependent. Temps shift towards albite corner with increasing pressure. The melting experiments on the granitic system clearly show that dry granite solidus has a positive slope while wet solidus has a negative slope. This helps us to understand as to why granites are most abundant plutonic rocks while basalts and not rhyolites are most abundant volcanic rocks. In the case of dry melt positive slopes, more heat is needed to produce dry magma, that is nearly 1000 degrees centigrade, which therefore originated deep within the crust. When the dry granite melts arise, it is erupted as a rhyolite and volcanic products. The wet melts negative slope, although produced at lower temperature 650 to 700 degrees centigrade and at shallower depth, that is nearly 15 to 20 kilometer within the earth, cannot rise far before crystallization. That means that wet melt will never be erupted as acid volcanic. On the contrary, the hot water under saturated silica magma may be able to ascend to the such higher crustal level. This melt, if tonalitic in composition, is likely to produce granite by fractionation, but leave the lower crust anhydrous dominated of gammolites. Crustal melting and granitic magma begin with introduction, followed by crustal melting and granitic magma, pressure, temperature and water rich fluids and partial melting, experimental work and origin of magmatites and granites. Understanding granitic melting experiments, when we can conclude that magmatites usually form at upper amphibolite phases when muscovite is no more stable in quartz bearing rocks.